So to introduce the electric field, let's actually start by stepping back and thinking about some of the basic things that we know about forces, right? So at this point, we should be pretty comfortable with the idea that a force is an interaction between two objects. In an everyday sense, it's how one object pushes or pulls on another. In the first semester of the course, we sort of split forces up into one of two categories. We said there's a set of forces that we can refer to as contact forces. And then there's this other set of forces that are non-contact forces. The electric force clearly sits in that category of non-contact forces. The gravitational force is also there. The magnetic force is also there. What makes these non-contact forces special is, well, how do you push or pull on another object if you're not in contact? And the answer to that question is that for these non-contact forces, the interaction between objects occurs through fields, which makes fields an incredibly important concept to try and understand, but it also means that it's a little bit more abstract, right? So that's part of why we start with forces first. Pushes and pulls are things that we've got a pretty good intuitive sense about. But now we want to talk about this underlying field and what that means, right? So just to highlight, if you take these three non-contact forces, gravitational force, electric force, magnetic force, replace force with field. Gravitational field, electric field, magnetic field, those are all phrases that you've heard of. So these are ways that non-contact forces interact. They interact via the field. If you take any one of the contact forces, say the tension force is an example, right? Well, you've never heard of a tension field. You've never heard of the friction field. Because these are contact forces, they don't need a field to interact through. Let's start by talking about the field that you know best, which happens to be the gravitational field near the Earth's surface. It points downward. Its magnitude is constant. It has a value of 9.8 meters per second squared. So when we've talked about the Earth's gravitational acceleration, it is an acceleration. It has units of acceleration, but that's another way of talking about the Earth's gravitational field. Well, what happens if you take a mass and put it in that gravitational field? It feels a gravitational force. So what's going on here is that you have a mass, the Earth, that creates a gravitational field. Then when you place a second mass into that gravitational field, it's attracted to the Earth through the gravitational force. The equation that explains that is the one that we used all semester long to calculate the gravitational force, right? It's F equals mg. It's just there's more meaning there than what we indicated through most of the first semester course. It's telling us that the gravitational force on that particle that you put in the Earth's gravitational field is equal to the mass of your particle times gravitational field strength. So in this case, times 9.8 meters per second squared. So let's take that same idea, because this is how these non-contact forces interact through fields, and think about it in terms of electricity. Let's take two positively charged particles. So there they are, sitting in our picture. We know that because they have the same charge, they're going to be repelled. So the charge on the right is going to be pushed away from the charge on the left. So it'll feel an electric force that points to the right. The charge on the left will be pushed away from the other charge. So it'll have an electric force on it, pushing it to the left. So again, these two charges aren't in contact. So where do these forces come from? How are these charges able to push and pull on each other? The charge on the left, let's think about that one first. The charge on the left creates an electric field. So charges create an electric field. Notice that in this case, that electric field is in the space all around it, including at this particular place that we've labeled point P. Now, why do I care about that particular point P? That's where I'm going to choose to put the other charge. So my second charge, I place it in the electric field at a point in space due to the first one. And in this case, it's going to be repelled from that first charge by how it interacts with the field. And here's the equation that explains that interaction. So the electric force on the charge that I place in the electric field is going to be equal to what's the charge times the field strength. Okay? So this is the idea. Now, of course, both charges are repelled away from each other. So how does that happen? Well, it's not just the charge on the left that's creating a field. The charge on the right also creates a field. It is a charge. Charges create fields. So what you have here is you have each charge creating its own field, and then the other charge responds to that field through an electric force. So the charge on the right gets repelled because it feels the field from the charge on the left and is pushed away. The charge on the left is repelled because it feels the field created by the charge on the right, and in responding to that, gets pushed away. So the big idea here is that the electric field describes how a charged particle influences the space around it. That's what the field is. It's a description of how that charge influences space. So a charge is going to create an electric field. That's how it's influencing the space around it. And then when you place a second charge in that field, it's going to react to the field through the electric force. Okay? And again, this is the equation that explains how those two things relate. All right, that's the big idea. So up until now, we've been working problems like this, right? So here we've got three charged particles. They're sitting in the XY plane. We're told where they are. We're told what their charges are. And so the question asks, what's the magnitude and direction of the net electric force exerted on particle 1 by the other two particles? We've worked that problem as a force problem. But the idea is, how does this relate to this field idea? Okay, that's the question. The way this idea works is it says, this question we've worked in talking about the net electric force, we can reframe it by thinking about there are two charges in this picture that we're going to label source charges. These two charges are responsible for creating an electric field in the space all around them, including at the place where we have placed our test charge. So by thinking about the electric force on particle 1, that tells us that particle 1 in this case we can think of as our test charge. And so what we're really interested in is what's the electric field created by our two source charges at the point where we put particle 1. Charge 2, charge 3, they're going to create an electric field. That electric field will be all through the space all around them, including at point P. And so one way that we can reframe this problem is to say, instead of thinking about the magnitude and direction of the electric force on a particle at point P, what if we went and calculated the more fundamental thing? Let's calculate the magnitude and direction of the net electric field created by these two particles at that point. So what that's going to allow us to do is say, we can figure out how our two source charges are influencing the space around them, including at point P. If we then want to know what the net electric force would be on charge Q1, we have an equation that lets us figure that out. So this equation tells us that the electric force on charge 1, when we place it at point P, is going to be equal to whatever the value of charge 1 is, times what the electric field is at point P. Now the nice thing about this is, when we worked it as a force problem, because it depended on charge 1, basically if we wanted to change charges, we'd have to go work the problem again. But once we know what the electric field is at point P, we can basically figure out what the electric force is on any charge, right? Make Q be whatever you want. Take any Q you want, put it at point P. This equation is going to tell you, if you know what's going on with the electric field, here's how you can figure out what the force is for any charge that you place at that point in the field. Okay. So that's the idea, is that charges form fields, and then when you place another charge that we'll typically label the test charge at a point in that field, it responds to the field through the electric force.